says I'm live, but am I alive? Yeah, it says so. I don't know. It's not playing back any of the things, but let's presume that I'm alive. Let's presume that you can see all this. It is presumptive, but maybe it'll work. Where's my pen? Oh, here it is. Okay, so I'm going to reload the page. They made me go buy an attachment to plug my computer into the Ethernet. Like a troglodyte, like a wingless angel, I have to plug my computer into the Ethernet. But through this, we can see it. Okay, now the movie recording still looks like butt. Is it live? It's... I'm not sure. Also, what's up with this recording? Give me a second here. How come you're still there? Good. Okay. So it is, I think there's a lag, but it says the stream is healthy. So let's go back. I was doing page 204, question 7. A turntable rotates clockwise at 78 rotations per minute. A speck of dust on the table is at 40.45 rad. And, okay. Well, things are improving. Yeah, there's a lag on the video, but it's okay. It's still very gross. You can't see it good. Why can't you see it good? You can see it good in this thing. I don't know. Okay. Alright, that's refreshed, so you can kind of read that. Welcome to the beleaguered stream. I finally got up and running. Right, so a turntable rotates. A speck of dust starts at this one place. Where is it? 8 seconds later. So to answer this, we need to start by converting from rotations per meter into radians per second. So I'm just going to multiply by 1 here. The trick here is I want to go from rotations to rads. There's 2 pi rads in 1 rotation. And I want to go from minutes to seconds. So there's 60 seconds in 1 minute. And that's how you put together your conversions. And then you multiply them all out. 78 times 2 times pi divided by 60. 8.17 rads per second. Okay. So that's question 7. Oh wait, no, we're not done. It says that there's an angle, a thing starts at theta initial is equal to 0.45. Where does it end up? So one thing we've been trying to impress upon ye is this idea that the mathematics for describing angle changes is essentially the same as it's always been, as it is in linear time. Your position, angular position as a function of time, is initial angular position plus angular velocity times time. So it's 0.45 plus 8.17 times, how much time has elapsed? 8 seconds. 0.45 plus 8.17 times 8. So that's 65.8 radians per second. I'm going to factor out the pi just so I can see what that looks like. So divided by pi. So it's 20.9 pi radians per second. All right, so the idea here is that as you go around the circle, your angle changes. And it can be bigger than 2 pi, obviously. So let's see. 2 pi, 4 pi, 6 pi, 8 pi. All right. So in other words, we can think of it. We can break up this number into some multiple times 2 pi plus plus some other number. Okay. In this case, it's 10 times 2 pi plus 0.9 pi. Okay. So this means I've gone 10 times completely around plus an extra that. So theta final is equal to 0.9 times pi. But that's usually I don't actually care if you do this step. But it says that the answer should be between 0 and 2 pi. So that's why I had to argue through this. As far as I'm usually concerned, this answer is absolutely satisfactory. It takes a little bit of interpretation to deal with it, but I don't care. Question 8. All right. Question 8 goes like this. A fast-moving superhero in a comic book runs around a circular 70-meter diameter track 5.5 times in 3 seconds. What is her angular speed in radians per second? Okay, so let's see. You got a circular track, and then your superhero starts out somewhere and goes 1, 2, 3, 4, 5.5. So delta theta is equal to 5.5 times around. Let's put that in radians. 1 time around is 2 pi. So it's 11 pi radians. That's how far you went. It took you 3.0 seconds. This is a very funny question. A fast-moving superhero in a comic book runs around a circular... What an exciting comic book. My name is Trackstar. It was created when lightning hit a UFO above a track meet. Angular velocity, assuming constant angular velocity, it's like that. 11 pi over 3, so that's 11 over 3 pi rads per second. We can calculate that number. This is 11.5 rad per second. Okay. Not the best superhero, but a surprisingly interesting comic. It's all about doping. 18. A 20-gram block on a 50... Oh, wait, hold on. Oh, okay. So in the last question, they told us it was a 70-meter diameter track. But that doesn't actually factor into the question at all. So I was like, wait, I thought they told us the radius. Yeah, so they tell us the diameter, but that doesn't matter because we're talking about the angular position. Okay, so 18. 18, a 200-gram block on a 50-centimeter long string swirls in a circle on a horizontal frictionless table at 75 revolutions per minute. All right, so you got your string. String is how long? 0.5 meters. And then your mass, 0.2 kilograms. And then it's going in a circle. Woo, circle. All right. So it's got a velocity like, I don't know, like that. Okay. So they give us some information and then they ask us questions. So what information do they give us? They give us an indication of how rapidly it's moving. 75 RPM. So let's convert that into... So this is an angular velocity, but it's in terms of complete rotations instead of radians. So let's convert this to radians. Rev per minute. So I want it in radians, and I want to get rid of the revolutions. There's 1, 2 pi. And I want it in seconds instead of minutes. 1 minute is 60 seconds. And then you calculate the value. 75 times 2 times pi divided by 60. 7.85 rad per second. That's the angular velocity. All right, so it wants to know how fast you go. there's a relationship between how fast you're moving and the angular velocity, which is omega times r is equal to v. 7.85 times 0.5 is equal to 93 meters per second. That's how fast you're going. 18b, what's the tension of the spring? Alright, let's draw a free body diagram. Here is the Bach in motion, here's the string. Okay, so tension goes like that. There's a normal force on the table, and there's a weight from gravity. Okay, so I don't want to... So what do we know about the acceleration? The acceleration is going to be pointed towards the middle as well. We know how strong the acceleration is going to be. V squared over r. Let's calculate that. 3.93 times 3.93 divided by 0.5. So its acceleration is 30.9 meters per second squared. So F net is going to be the mass times that. So 0.2 times A. 6.18 newtons. And you note that there's only, so the net force is pointing in that direction in this diagram towards the string. It's the only force that's pushing horizontally is the tension force. So 6.18 newtons. Okay. A quick note, and I'll say it over again. If there are any specific questions you'd like to see me go over, you can ask them in the live chat feed, and I will go through with them. And I'm surprised that the Ethernet is so good. I'm depressed because I like the wireless, but this is working very well. All right, next question, 28. Question 28 goes like this. The centers of a 10 kilogram lead ball and a 100 gram lead ball are separated by 10 centimeters. What gravitational force does it exert on each other? All right, so here's your big ball, 10 kilograms. Here's your little ball, 0.1 kilogram. And the distance between the two, or the distance between the two middles, is r is equal to 0.1 meters. So let's put all this into G, big M, little m, over r squared. George R.R. Martin. No, wait, that's not what it says. No, that's not it. Hold on. 6.67 times 10 to the negative 11. That's the gravity constant. The mass of the big object is 10. The mass of the little object is 0.1. And the radius is 0.1 all squared. And you put this into your calculator and you get 6.67 E minus 13 newtons. So the force is very, very, very small. What's the ratio of the gravitational force to the weight of the 100 gram ball? Okay, so the weight of the 100 gram ball is 0.1 times 9.81, so that's 0.981 newtons. And then what's the ratio of 6.67 E minus 13 over 0.981? 6.67 E minus 13 divided by 0.8981. So that's 6.8 E minus 13. Hooray! There's very, very, very little attraction between two objects on your desk. which isn't surprising at all, because objects on your desk don't usually tend to fall towards each other. 36 now. Hold on, I'm going to drink some water. Uh, 36 goes like this. Satellite A orbits a planet with speed 1,000 or 10,000 meters per second. Satellite B is twice as massive as Satellite A and orbits at twice the distance from the center of the planet. What's the speed of Satellite B? Let's draw a picture. Big M. Here's A. So A. I'll call that RA. And here's B. And it's going in a circle as well. This distance here is to RA. Okay. So if something's in orbit, there's only one force on the object. F net is little m, big G over r squared, right? This force is responsible for accelerating you towards the middle. So F net has to be m v squared over r. So in other words, what I'm saying is that this value and this value have to be the same number. Little m, big M, G over r squared, little m, v squared over r. Let's play the cancel game. Now I'll just recopy it with stuff canceled out. The m's cancel, the little m's, and one of the r's cancels. This is the relationship between how fast they're traveling to go in orbit and the radius of their orbit. Okay, so in this question, they say satellite A orbits with a speed of 10,000 meters per second. All right, so at mg, at radius RA, the speed here is 10,000 all squared. And so the question here is, what's the speed at satellite B? Satellite B obeys its RB, VB all squared. So we want to know what that value is. So the deal is that I already know some of the things, right? Like for instance, I know that RB is 2RA. So you can rewrite this. Okay, so I'm trying to find VB all squared. Mg, I don't know what the mass of the planet is, and I don't know what RB is, but I know RB is 2RA. And I know that this whole thing is equal to 10,000. VB all squared is equal to 1/2 10,000 all squared. I'll put this into my calculator. 7071 meters per second. That's how fast satellite B is going. Betty C says, I'm scared for the midterm. Hi. Hi, Betty C. Okay. I'm sorry that you're scared. I would like you to either try along the questions that we're doing, or alternatively, go through the book and try to figure out questions or explanations you'd like to hear me give. And so in a question or two, I'll look back at the live chat, and then I will address your specific questions. The key here is to be strategic. Can you figure out what it is that's bugging you? Everybody's scared of everything all the time. Us, midterms, everything. I'm scared to mark the midterm. No, wait, I don't mean that. I mean, wait, I make somebody mark a marker mark it, so I'm not scared of marking this one. But moral of the story is, ask yourself, what types of questions am I having trouble with? And then look up a question or two in the book. Try to find questions that you'd like to see me do, and then we'll try them. So right now I'm focusing on stuff that was from last week and the week before. So circular motion, mostly, in various forms. Questions involving circular motion. But yeah. Yeah. So how about that? Okay. Next question. See, that was 28, right? No, that was 36. Oh, cool. Question 37. 37 says the space shuttle is in a 250-mile high orbit. What's the orbital period in minutes and its speed? Okay, so this question is actually pretty annoying because all of you are like, what's a space shuttle? So let's see. Around 2003, I think, which was it? Was it the Enterprise? One of the space shuttles burst into flames coming back to Earth, and after that, all the space shuttles were grounded. Space shuttles are really cool things. They look like this. Yeah, cool. And they have little windows at the front. And they have a little fin at the back. And then they've got great big thrusters on the back. And they have a great big cargo bay. And we used to shoot them into space. And they're great because they're reusable. And then you can land them like an airplane instead of dropping people in the middle of the ocean. But we don't use them anymore because they were out of date when they started blowing up. And so we stopped using them. It was very sad. It's funny. I and all my Canadian cohort really wanted to be an astronaut. Ever since we were kids, we were like, yeah, let's be astronauts. My American friends don't, because when they were in grade 3 or 2 or 1 in school, NASA had an education program where they used to show kids shuttle launches and get everybody excited. And so there was a shuttle called the Challenger, and it was really exciting, and everybody was super pumped to see it. Because there was like a school teacher was one of the astronauts. It was a very popular crew. So everybody's very excited, then it exploded in midair. And so it kind of terrified all these children. None of these children wanted to grow up to be astronauts. It's kind of sad because I really like the shuttle. Okay, so that's what a shuttle is. It's in 250-mile high orbit. So here's the shuttle. What do they mean by that? Usually when people are specifying these questions, they mean that distance is 250 miles. Because they're using the word high, and that usually indicates off the ground. So I got to look up the, miles. 250 miles in meters. 250 miles in meters is 402,336 meters, and the width of the Earth, the radius of the Earth, is is 6371 E6 meters. Here, I'm going to write this last one in scientific notation. 4.023 E 5 meters. So even though it's 250 miles off the ground, the bulk of the distance, its orbital distance, comes from the radius of the Earth. So I'm going to calculate this distance here. That is 6.371 E6 plus 4.023 E5. All right, here, hold on. 6.371 E6 plus 4.023 E5, which is 6.77 E6 meters. Oh, good work, Bethany. My wife did a plumbing test today, and she was sad, but she got a 90 on it. So, just like how your gal's going to get 90s on your midterms. Okay, I also need to know the mass of the Earth. Oh, it says here on Google. Earth is equal to 5.972 E24 kilograms. Okay. So I'm pretty much just going to repeat this calculation to figure out the answer to all these questions. Okay, so the deal here is that there's only one force on our space shuttle when it's way out here. There is a force, and the force is the weight of the space shuttle. We calculate the weight using a different formula than we do on the surface of the Earth. So the weight here is little m, big M, g over r squared. I don't know the mass of the space shuttle, but I know the other ones. So this is going to be little m times, and I'm going to multiply them together. 5.972 E24 times 6.67 E minus... divided by the radius. 6.77 E6. All right, so this gives us m times 8.69. You know, gravity up there, so this thing here is actually the acceleration due to gravity in free fall. The weight 250 miles above the Earth isn't that different from the weight down on the Earth. Okay, so that's the only force acting on it. And so F net is equal to m acceleration. Do I know about the acceleration? Yeah, you're going in a circle, so the acceleration is v squared over r. And so when I put these together, weight is equal to ma, you end up with m 8.69 is equal to mv squared over r. Now I cancel the m's, and I can calculate v. So I move the r to the other side, so 8.69 times 6.77 E6 square root, answer 7,670 meters per second, which is very, very fast. The period can be found by dividing the distance, 2 pi r around the circle divided by v. So 2 times pi times 6.77 E6 divided by 7670. 5546 seconds, and it's asking for this in minutes. So I'm going to divide that by 60 to see how many minutes it is. So this is 92 minutes. Every 92 minutes. So every hour and a half it goes around the Earth once. That's pretty fast, right? Yeah, so that's that question. I see what people have to say in the YouTube. Okay, Stephanie Duncan just asked, is the midterm going to be structured like the practice midterm in the sense it is fewer questions but are worth more? Sorry, this question is about the question you're doing. That's okay, Stephanie. So to answer your question, I don't know. I think there's going to be some longer questions. Yeah, longer calculation questions. At the start of the term, we focus a lot on kinematics. So, you can't do there that much other than kinematics questions. Whereas at this point, you're essentially setting the table for all the things we're doing right now, like vectors and stuff like that. So at this point in the game, you should be capable of a variety of really interesting calculations. And so we're probably going to ask you some, well, medium level difficulty calculations. I don't want to ask you really hard ones because nobody gets those right, and then I have to feel bad. But I don't want to ask you ones that are too simple. So they're probably going to be a bunch of medium level long answer questions, yeah. You know, I reserve the right to give you some theory questions too. But yeah, it's probably going to be more like the practice midterm insofar as long answer questions. All right, let's get back to it. This was question 37. Next, question 40. It looks like an egg. Okay, so question 40 is, how fast must a plane fly along Earth's equator so that the sun stands still relative to the passengers? Oh, this is a great question. In which direction must the plane fly, eastwards or westwards? Give your answers in kilometers an hour and miles per hour. I'm not going to do miles per hour. The radius of the Earth is 64,000 kilometers. Okay. Here's the Earth. Now I know it's not true that the sun is going around the Earth, but it sure looks like it. It looks like the sun is going around the Earth in a big circle, right? What's the period of that journey? The amount of time it takes is 24 hours, which we can write in. Let's see. Hold on. What kinds of things do they want in? They want this question in kilometers per hour and miles per hour. Okay, so leaving it in miles is good, I guess. So the idea here is, if you are in an airplane, let's draw your airplane here. Here's my airplane. Boop, boop, boop. All right, looks like a shuttle. If your airplane goes around the Earth so that the sun is always overhead, then the airplane must have the same period as the sun does. Does that make sense? So the Earth has to go around, the plane has to go around every 24 hours. The speed is going to be 2 pi times the radius that the plane is traveling around, which is given. Where's it given? Okay, 64,000 kilometers, 6,400 kilometers. So that's 6.4 e 6. Hold on. E3 kilometers divided by the amount of time, 24 hours. The result is something that's going to be in kilometers per hour, which is what they desired. 2 times pi times 6.4 E3 divided by 24. And the answer is 1,675 kilometers an hour. Planes can't fly that fast. No, I don't think they can. So, yeah. Incidentally, do they have to fly, east or west to get this doing? Well, they have to match the sun. So which way does the sun go? The sun starts out in the east and goes to the west. So, if I'm standing here on the Earth and the sun's going around that way, the sun will be in the east over here and travel all the way to the west over here. And so the airplane has to do the same thing. The airplane has to fly east, west. Oh, I don't know why I'm so tired today. I'm really knackered. All right, that's the end of that question. Nobody has any questions in the live chat, so let's move on to question 49. Huh. Okay, this question is fantastic. It's a question we saw on the midterm, on the practice midterm, I think. So one of the reasons some of you might be very scared of the practice midterm is, the method that it uses to break down Newton's law questions is exactly the same as the way we did. And the method that they use to analyze circular motion is exactly the same as ours. That said, we spent a few more days doing circular motion questions than we did in this class. And so the level of sophistication of those circular motion questions are actually pretty great. And this is one that's quite similar to it. It goes 1 meter, and there's a ball, and the ball's going in a circle like that. Okay, so what is the tension in the string? Well, what do they tell us about this thing? This is a full Newton's law question. 0.5 kilograms. That's a 1 meter long rope. And the horizontal circle is radius. So that is moving around a circle in is 0.2 meters. Okay, so we have to analyze this, and it won't be easy. It's asking for us for the tension in the string. What do we know about the string? Here, hold on. Give me a second. All right, so what do I know about this? What do I know about the forces? What do I know about the motion? Let's start with the motion. What kind of motion is it? It's circular motion. Uniform circular motion, specifically constant speed. And that means it accelerates towards the middle at v squared over r. I don't know how big the acceleration is, and I don't know how big the velocity is, but I do know, here, let me take a big step back and I'll draw a schematic. Here's our ball. Okay, here's the rope. I'm going to draw an x and y axis just to help us out. So let's say the x-axis is in this direction, positive x, positive y in that direction. Okay, so we know based on a description of the motion that the acceleration in the y direction is 0. All the acceleration is in the x direction, and it's circular motion, so it's going to be v squared over r. Okay, that's all I know. I don't know how big the acceleration is. I know how it's related to the speed, so I wrote it down there, but I don't know much else. Now, I can calculate the net force. The net force in the y is 0. The net force in the x direction is 0.5 times ax, which is 0.5 divided over 0.2. In the end, we get 2.5 times v squared, pointing towards the middle. All right. Doing this question requires that we do these steps first. Now, let's sort out all the forces on the ball. There's gravity, and there's a tension force. Okay. So, Here's the first big issue. It's that, okay, do I know the weight on the ball? Yes, I do. Weight in the x direction is 0. Weight in the y direction is 0.5 times 9.81. 4.91 minus newtons. So then, the question here is, what do I know about the tension force? The issue here that makes me really worried is that it seems to me like both of these can take any value they want, right? You can have a big tension towards the middle and tension up, but that's not quite the case. They both have a lot of different values they can take, but the two values aren't independent of one another. If I knew what the tension in the x direction was, I could figure out the tension in the y direction, and vice versa. Why is that? Well, the answer is because the tension has to be given at the same angle as the rope is. So from geometry, you know that this is a 1 meter and this is 0.2 meters. And so you can figure out what theta is using inverse trig functions. Arc cos 0.2 divided by 1. So that's 78.4 degrees. So I don't know how big the tension is, but if I did know it, I could use this angle, which we got from the position of the rope, to figure out what Tx and Ty are. T times cosine of 78.4, T times sine, 78.4. Good. Now I can put all of these terms together. This one, this one, this one, this one, that one. So in the y direction, they all add up to 0. There's a force of gravity and a force of tension. 78.4. Good. That looks pretty good. I'm probably going to use that to calculate how big the tension is. And then in the in the x direction, total force 2.5 times v squared is equal to, weight isn't in the x direction, but t cosine 78.4 is. So let's use these equations and solve them. First one, that one tells me what t is. It's for 2. So that's 5 newtons of force in it. And so 2.5 v squared is equal to T times that, so you multiply them together and you get 1 Newton. So V is equal to 0.635 meters per second. Okay, so what's the tension in the string? There's the answer to that. What's the ball's angular velocity? Well, we just calculated what the velocity was. The angular velocity is going to be v over r. So it's going to be 0.635 divided by the radius of the circle it's traveling in, not the string. So 0.2. 0.635 divided by 0.2. 3.18 rad per second. Make sense? Okay. So now let's do question 51. It's tons of fun. A 0.2 kilogram puck on a frictionless horizontal table in figure 6.51 is connected by a string through a hole to a hanging 1.2 kilogram block. With what speed must the puck rotate in a circle of radius 0.5 meters if the block is to remain hanging at rest? This is actually a really neat question. They're really hard to do on tests. I mean, they're really hard to rate as test questions, which makes me really sad because I adore them. So you got a thing. It's a thing. And it's moving in a circle. Moving in a circle. Okay. In this case, what is providing the acceleration? What force is providing the acceleration to keep this thing going in a circle? Well, you attach a little rope to the thing and you put the rope in the hole. And then you hang from it another mass. And this is a really neat question because the force of tension in this part of the question, the force of tension keeps your mass from falling. In this part of the question, that same force of tension causes the object to move in a circle. Does that make sense? So it's like, really, you can go up to a little kid and be like, hey, what force is holding this object in the air? The short answer is the tension force, but that's unsatisfying. What is it that how is this thing pushing on it to cause this guy to stay in the air? And the short answer is this person's inertia as it moves. Its refusal to accelerate at any acceleration except for the very specific one keeps this thing in the air. It's inertia. Inertia is what holds it in the air. Isn't that bonkers? Okay. So, what'd they give us? This is 1.2 kilogram, and this one is 0.2 kilogram, and this is 0.5 meters. Okay. And so the question here is, what speed does that block have to go? So this one's pretty fun. What's up, Jody C? Why'd you say whoa? Hold on. Somebody just flipped out just a little bit on the live chat. I gotta see what this is about. Jody C, what's up? I'm gonna elaborate this drawing while I wait for Jody C to finish answering. Oh, Jody C's. Yeah. Don't worry, everybody. Jody C just thought it was cool. Thanks, Jody. If you think this is cool, you should keep on doing your degree in physics because there are many cooler things than this out in the world. Okay, so how do we analyze this? You do it in two parts. The trick to these tension things is to relate their motion, but also relate the tension force between them. And aside from that, consider them as two different objects. Okay, so on the mass on the table, they're going in a circle, right? Constant speed. What does this tell us about the acceleration? Okay, so let's draw a little picture of the mass on the table and the string. All right, and let's get some axes up here. How about X is in this direction and Y is in this direction? And coming towards us. Okay, so so what do we know about this thing's acceleration? Its acceleration in the y direction is 0. I'll call it table mass. Its acceleration in the x direction is v squared over 0.5. Okay, I know which direction it's pointing towards the middle. In terms of this axis, that's a positive x direction. Okay, so f net t in the y direction is 0. F net t in the x direction is mass times all that. 0.2 divided by 0.5. So that's 0.4 v squared. Okay. So that's what we know about the motion of the top one. Well, let's just keep on with it for now. What else do I know about it? Let's draw a free body diagram on it. There's the normal force, and gravity, and the tension force. I don't know how big the normal force is, but I know its y component is, its x component is 0. I know how big the gravity is, though. 0.81 times, what is this, 0.2? Minus 1.96 newtons. And the tension force in the x direction, I don't know how big that is, so we'll call it T. Okay? So if I want, I can put all these equations together, right? This is the sum of all the forces in the y direction. So y components, that's 0 is equal to n minus 1.96, which tells you that n is equal to 1.96. Let's not pretend that there's anything too wicked going on here. 0.5, no, 0.4. V squared is equal to however big the tension is. I don't know how big the tension is. Now, the next part of it, that's the hanger. I'll call it mass hanger. Okay, so what's its acceleration? Its acceleration in the x direction is 0. Its acceleration in the y direction is 0. At this point in the game, you're probably like, hey, I've seen you do these questions before. Usually we link up what the accelerations in these two cases are. They're related. How come this one has a non-zero acceleration, but this one, both the accelerations are 0? That's a good question. The answer is, it has to do with the type of motion. Like I said, you always want to kind of imagine these things. This one here is not moving. Its velocity is 0 and it's staying 0. This one up here, its velocity can change. If this one was moving, though, it would mean that the length of the chord here would be changing, right? Increasing or decreasing. But the length of the chord isn't increasing or decreasing. It's staying the same length. The distance from that to the top of the table is the same length. Of course it is. So how does that manifest on the top of the table? That corresponds to the distance between here and here on the rope is always the same length. So it's not that this guy can't move. It's not even that that guy can't accelerate. It's that this one here, if this one here isn't moving, the one on the top of the table can only move in a circle. All right? So this one has accelerations. So F net hanger on is equal to 0 in the x direction. F net hanger on in the y direction is equal to 0. Let's label all the forces. There's gravity and tension force. T in the y direction. Weight in the y direction is minus 9.81 times 1.2. I don't know how big the tension force is, but I do know that it's the same for both of these. Yeah? Okay, so I can put all this information together with this information, and you get 0 is equal to t minus 11.77, which tells us that t must equal 11.77 newtons pulling up. So those forces will balance. And I can use this to answer this. 0.4 v squared is equal to 11.77. So that's 11.77.4 square root. Answer 5.42 meters per second. Got to go pretty fast. All right. So that's question 51. That's the end of one object moving in a circle. Time to move to the circular motion questions. Oh my god, it's going to be so late here. All right. Quick reminder that if there are any questions you'd like to see me do specifically, you can ask about them in the live chat and I'll make a note. And then I'll do them whenever I feel like it. Page 236. Question 2. Okay, so actually, so as a quick note, I'm going to do a couple torque questions in this just because we covered it last week. So this question isn't a torque question, but in a question or two we'll reach the torque questions. And it's because you got to be able to do torque stuff eventually, but the torque stuff isn't on the test. So if you're super worried about the torque stuff, don't be worried about it. Not yet, at least. Okay, so question 2. A computer hard disk starts from rest and then speeds up with an angular acceleration of 190 rads per second. This is, okay, this is an exceeding amount of rad. I mean, you got to be so cool to get that much rad, which is why older computers overheat. They're just not cool enough for the amount of rads that we need. Okay, it needs, so the final angular speed is 7200 RPM. So before we can even do the question, we need to convert this into radians. So RPM stands for rotations per minute. So I want the minutes to turn into seconds. So I multiply it by 1. And I want the rotations to turn into radians. There's 2 pi radians per 1 rotation. And this stuff will cancel out. And you get okay. So let's talk about what the question asks. The question says, how many revolutions has the disk made 10 seconds after it starts up? This is kind of a tricky thing. Let's draw it as a cartoon. T is equal to 0 seconds. T is equal to 1 second. T is equal to, I don't know, question mark seconds. T is equal to 9 seconds. T is equal to 10 seconds. All right. So initially, the disk is at rest. From this time to some other time, the disk starts speeding up. So it spins faster and faster. Speed up. And then at this time it reaches the max speed and W final. And then it rotates with constant rotation. There's a baby outside my office. And then it just keeps rotating until the end of the thing. So why do I bring this up? I bring this up because we don't know how long it takes to reach full speed off the top of our head. And the equation describing constant rotational acceleration, which is delta theta is equal to omega initial times t plus alpha over 2t squared, is a different equation than the equation describing constant rotation. Delta theta is equal to omega times t. Okay? So because we don't know when the transition happens between the two, we don't know how to quite tackle this problem. So the first step in this is to figure out when the transition between the two takes place. So how much time does it take to reach full speed? Well, we know all sorts of things here. We know the initial velocity, we know the acceleration, we know the final velocity. Right? So let's plug this in. We know the final velocity is 5.4. We know the initial one is that, 190 times t. So four seconds. Okay, so we know, in other words, to summarize, we know that it undergoes constant angular acceleration until the 4-second mark, and then for the last 6 seconds, it rotates at constant angular velocity. So now we can use the various equations. Before we go on, this is this is new and it's weird, right? Rotation, radians per second. It's weird. Granted it's weird. I know that it's weird. But in spite of it being weird, it's mathematically very familiar, because at the start of the term we did constant acceleration and constant velocity systems. And now we're dealing with essentially mathematically the same thing. Constant acceleration, constant velocity. So let's find out how much angle it does in the first 4 seconds. From t is equal to 0 until t is equal to 4 seconds. The initial angular velocity is 0, and the angular acceleration is 190 divided by 2 times 4 seconds. So this is 380. And then from 4 seconds until 10 seconds. It's moving with constant angular velocity, which is 754 times t, which is 6 seconds elapse. 754 times 6. 4, 5, 2, 4. And so the total angle is the two added together, 380 plus the other one, 4904 radians. So the question asks, how many revolutions? This is the distance in radians. 1 revolution is equal to 2 pi radians. So to find the revolutions, I'm just going to divide this number by 2 pi. 780 revolutions. You see? Okay, next question. Question 3. The crankshaft in a race car goes from rest to 3,000 revolutions per minute in 2 seconds. Initial is 0. Final is 3,000 revolutions per minute. Let's put this in radians per second. Minutes turn to seconds. Revolutions turn to radians. 2 pi 1. 3,000 divided by 60 times 2 times pi. 314.1 rad per second. Alright. So we want the angular acceleration, so it's going to be final velocity minus initial velocity divided by delta t. So that's 314.1 divided by 2 seconds. 157 rad per second squared. How many revolutions does it make when it's reaching this? Okay, so delta theta, that's initial velocity plus times t plus 1/2 alpha t squared. We know a lot of these. The initial velocity is 0. The amount of time it takes is 2 seconds. 1/2 times 157 times 2 squared. So that's 314.1 rads. And I want the number of revolutions. So I'm going to divide this by 2 pi. 314.1 divided by 2 times pi. 50 revolutions. Any questions? There's no questions in the stream. Man, it costs $40. This thing that lets me get on the internet with the computer, even though wireless is a butt today, and it's going so fast. I'm depressed because I didn't want to buy anything, but I'm impressed because it worked well, so I'm de-impressed. Okay, question 5. Balls are attached to light rods and can move in horizontal circles. Well, that's fun. Rank in order from smallest to largest the torques above the center of the circles. Explain. All right, so most torque, least torque. I'm going to copy out the drawing. Actually, hold on. I'll draw the forces later. All right, okay. And the last thing I need to do is draw the forces. So this force is a standard amount of force. This force is twice the standard amount of force. This force is the standard amount of force. No, standard amount of force. And this one's twice the standard amount of force. Now I need to rank them. Okay, so you don't know all that much about torque at this point in the game. I pointed out in class that it's a lot like leverage. The concepts are the same. Or rather, the phenomena is the same. The application to the concept is slightly different. But the idea here is the larger the force is, and the farther it is from the middle, torque is equal to distance from the middle times the part of the force that's perpendicular to the axis, to the radius, to whatever you're pushing on. Okay, so that means that this one is going to be smaller than that one. This one here has more force, so it's going to offer more torque. What about this one here? Well, this one offers the same amount of torque, but this radius is larger, and the larger radius means there's more like leverage, there's more torque. How much more? This one's going to have, wait, hold on. This one's going to feel twice as much torque as that one. Similarly, this one feels twice as much torque as that one. So this one and this one are the same amounts of torque. Double the original. So I guess they're going to be the same strength. All right. What about this one? This one is going to be even stronger than the other two, because this one not only does it have more leverage, but the force is twice as strong. Does that make sense? All right. So our answer is a ranking that looks like that. Which is fun. I don't usually do ranking questions on the online homework. All right, so next question is question 6. Question 6 goes like this. 6 forces, each of magnitude force or 2 force, are applied to a door as seen from above. Ranking order from the smallest to least the torques about the hinge. All right, so the torque, as we said in class, is the distance from the middle times the part of the force that's perpendicular to the arm. Or alternatively, length times force times sine theta, where theta is the angle between the two. I'm going to try to explain this without that, though. So here is our door. It's adorable. Okay. And here are the different forces we apply to it. That's 2F. Force out here. Okay, so the deal is that torque only takes place in context of rotation. If somebody gives you a torque question, it's always with regard to a hinge or a place that the thing is rotating around. In this case, we get a hinge. Each of these torques have a name. This one's torque 1, this one's torque 2, torque 3, torque 4, torque 5, and torque 6. Furthermore, this length here is L over 4, and this distance here is 2L over 4. Okay, so let's start tracking it. My first proposal is that tau 1 is equal to tau 3. Why do I think that? This torque here has twice the regular force, but is halfway down. This torque here is twice as far away but half the force. And so the fact that one is one half and the other is double means that when you multiply them together you get the same number. So I think those two are going to be the same. Furthermore, I think that torque 2 and torque 4 are going to be the same strength. And the reason is, it has to do with when you decompose these vectors into their vertical components. The part of the vector that's perpendicular to the door is the same in both cases. And since they're applied at the same location, and the perpendicular forces are the same, it should be the same amount of torque. Now, what about this last one? This torque is going to be really big. And this torque is going to be 0. Why is it 0? It's 0 because we're asking ourselves what the perpendicular component of the force is. This entire force is parallel to the line between the pivot and when you're applying the force. In other words, theta is equal to 90 degrees. Okay, so now let's sort these out. Well, T3's got to be bigger than T2, so this order seems right. T5 is really big, so it's probably bigger than them. And then T6 is 0. It's done here. Does that make sense? It makes sense to me. All right, I'm going to reiterate that if you want to see me do a question, feel free to ask. I'm probably going to be at this for another 10 minutes. So you've got 10 minutes to ask a question you want to see me do. Also note, torque is not on the midterm. So this stuff could be on the midterm. This stuff, this question's kind of hard, but could be. These questions, not on the midterm. Maybe on the final exam, not on the midterm. Okay. Why are you doing them? I don't know. You know there's life after the midterm. 12. What's the net torque of the bar shown in page 7.12 about the axis indicated by the dot? Oh, that's fun. So I want to find the net torque. So here's the bar to reproduce what we see. This is where you hammer a nail down and you can pivot around it. This here is 0.25 meters. And this distance here is 0.75 meters. And you're going to apply, in this case, two forces. A force like this, 10 newtons, which is perpendicular to the bar, and a force like this, which is 8 newtons. So I need to calculate the net torque, and so I'm going to label each of these. I'll call this torque 1, torque 2, and I calculate each of these torques. So torque 1 is going to be the distance from the bar to the distance from the pivot to where I'm applying my force. So that's 0.75 times the perpendicular component of this force. It looks like it's all perpendicular. So it's 7.5 Newton meters. Torque number 2, 0.75, because I'm applying a force at the same place. But this time, what's the perpendicular component of this? It's going to be 0, because it's parallel to the bar. So it's 0. So the net torque is plus 7.5. Cool. Okay. Number 13. What's the net torque shown in page 7.13 above the axis indicated by the dot? Okay, so I'll redraw that diagram. You got your bar. Here's your dot. This is 0.25. This is 0.75. That's in meters. This is in meters. And then there's two forces being applied. One of them goes this way, and it's 10 newtons strong. One of them goes this way, and it's 8 newtons strong. Okay. So, let's calculate the torque. I'll call each of these torque 1 and torque 2. Keep in mind that the torques are pointing in opposite directions. One of them's going clockwise, and the other's counterclockwise. And so in these questions, you need to, if we're going to find the net torque, we have to add things together. And that means that we need to figure out what signs things are. I'm going to use the convention. This way is positive. Counterclockwise is positive. Okay. So, torque 1. It's going to be the force. Wait, it's going to be the distance to the middle, which is 0.25 times the force perpendicular. It seems to me like the whole force is perpendicular. Okay. So that's 2. Yeah, that's 2 Newton meters. Torque 2, that's the distance, 0.75, times the perpendicular bit. Seems like it's all perpendicular. So that's going to be 7.5 Newton meters. So to add them together, I have to assign them signs, like I said. So which signs should these be? This one here is pulling it in the counterclockwise direction, so it should be negative. This one here is pulling it in the clockwise direction, so it should be positive. So the total torque is going to be -2 plus 7.5 is 5.5 positive Newton meters. So the overall torque will rotate to the counterclockwise. Okay, that's it. That's it for the questions I've, well, prepared. Prepared is quote-unquote prepared. I don't have anything else to show you today, but I'm going to sign off if you don't have any questions. So I'm going to wait around here, and feel free to ask me questions that you want to see me do. We've got a midterm tomorrow. Is there anything you'd like to review? I'm going to draw a bunny, and when I look up from the bunny, either there's going to be questions and I can answer them, or there isn't and I can go away. Actually, you know what? What's this like? Let's see. Oh, yes. All right. And nobody has any questions. So good luck studying for your midterm. Remember before you go that not all the questions, there's not going to be complete overlap between last year's midterm and this one. I mentioned before, last year had a different emphasis, and last year we hadn't done, at this point in the term, we hadn't done rotational motion, and there's a lot more rotational motion in this one. The details of the examples in last year's questions were maybe a little bit more sophisticated than this one. So keep that in mind when you're studying. Also get lots of sleep. Yeah, get lots of good rest tonight, and then do well in the midterm tomorrow. I'll see you all later. Bye-bye.